Hi, this is Maggie. In this video we're going to talk about the Iterator design pattern. The Iterator design pattern is one of the patterns described in the book published in 1995 called Design Patterns, written by the authors sometimes referred to as the Gang of Four. If you're planning on working as a software engineer, I recommend you read this book and any books you can find on using these patterns in the language or languages in which you develop. Python in particular has support for the iterator pattern that allows you to hook it into the for-variable-in collection syntax. We'll talk first about the pattern in general, and then about how to implement the pattern in Python. This association class diagram shows the objects, or you might think of them as object roles, in the iterator pattern. The first is an iterable, which is an object that can be visited sequentially. The most natural iterable to imagine is a list, which we can visit by beginning at index 0 and incrementing the index by 1 until we reach the index of the last element in the list. An iterator object basically keeps track of a location in that iterable structure. So if we're iterating over a list and we visited elements 0, 1, and 2 using the iterator, when we ask the iterator for the next element, it gives us the element at index 3, and then 4, until we reach the end of the iterable. The client is the object that is iterating over the iterable. So that is anything that needs to iterate over another structure, which could be many, many things because we are frequently looping through data to process it. If you think about the different programs we have written to iterate over a list, you'll have an idea of what the client might be. We've written many clients that use an iterator and iterable. This pattern has several benefits, besides that it is giving us a structure for accomplishing a very common task. One benefit is that the iterator is separated from the iterable. This keeps the iterable code confined to maintaining the data structure and not maintaining one or more indices into the data structure. The second benefit is related. We can define many different kinds of iterators. So we might write one that iterates over a structure forward, and one that iterates backward, and maybe one that applies a filter as it iterates. And we might have multiple iterators for the same iterable. Two different parts of the program might be processing the data at the same time, and each might be at a different location in the iterable. Therefore, it is practical to have the information about the location stored in a separate object, the iterator. There are a few methods that we write for each object taking on a role in the iterator pattern. For the iterable, we write a method to return an iterator. Let's call that getIterator. Although in Python, if we want to hook it into the for-variable-in collection syntax, we will call it something else. For now, let's talk about the general pattern. So the iterable, which is some sort of collection, returns an iterator that can specifically iterate over that kind of collection. The iterable will also have to give the iterator access to its data. So the iterator could copy the data, or the iterator could access it through a method of the iterable. So let's write accessor here for the iterable. And for data, the iterable contains some sort of collection. Now the iterator will have a next method and possibly a first method to reset it back to the beginning of the collection, and an isDone method, which will return true when it's reached the end of the collection. It has access to the iterable or its data, and it keeps track of the next element in the iterable. Now the client is just any object that has some sort of reference to the iterable and wants to iterate over it. So what does the client do? It asks the iterable for an iterator, and then it uses the iterator to iterate over the collection by writing while not iterator is done element equals iterator.next, and then doing whatever processing it needs to do with that next element. That's the general pattern. Now let's look at what the Python equivalent to these methods are. We'll start with the iterable. The special Python equivalent of getIterator is a method called _iter. There's nothing to stop you from doing this entirely by hand and writing getIterator or calling it whatever you want. You can implement this pattern without using Python's built-in support. But if you write special Python methods, then you can hook into some of Python's functionality. In this case, you can hook into the for variable in collection syntax. So we write __iter__, which simply returns an iterator that can iterate over the collection in which we write the method. To access a data element of the collection depends on the composition of the collection. There's no hard and fast rule because we don't know what kind of collection it is. You can write some sort of accessor, but if it's something we would like to index into with square brackets, and it's possible to pass in one argument describing a unique item, then we can write the __get_item___ method. This takes one parameter equivalent to an index in a list or a key in a dictionary and returns the element associated with that parameter. Now, looking at the iterator, we write an iter method which simply returns self as required by Python. And we write __next___ method. Now, this is a little trickier. We're going to return the next element, and we're going to advance the next pointer. In Python, the next method and the isDone method are basically combined into next. So let's look at a concrete example. I thought we would do something relatively simple, and that is to wrap a class around a one-dimensional list that stores data that is being analyzed. In our one-dimensional list, I would like to be able to represent missing data using some sort of code that indicates there is no data, such as NA or none. So a list of data might look like, if we were assigning either category A or B to whatever we're studying, A, NA, B, A, NA, NA, for example, where NA indicates missing data. And I would like to write an iterator that iterates over the data and returns only assigned values and skips the values that are equal to our no data code. So this program called datasetIterator contains the class wrapped around the dataset, but with methods that allow it to take on the iterable role in the iterator pattern. And really, it doesn't have much else because we're just illustrating the pattern here. So here's that class called dataset, and you can see it's quite small. It has two fields, data, which is a list, and noncode, which is a string representing that code that indicates the data element is missing or isn't coded. And we have an init method in which these fields get initialized from parameters, and then the iter method, which is part of our pattern. Remember, the iter method is Python's version of getIterator, so it's going to return an object of type datasetIter, which is our iterator that goes along with this iterable. We simply initialize an instance of the datasetIter and return it. When we look at the initializer for the datasetIter, we'll compare it to this argument list. The final method is the getItem method, which allows other objects to index into our dataset object using the square bracket syntax. And we just use the index that's passed to index into our data field because our data field is a list. So let's look at the iterator now, called datasetIter. This is the more complicated class because this is doing the work of iterating. This class has a field referencing the iterable object, dataset, and it also has a reference to what the no data code is, so it can ignore those entries when returning the next element. It has an index to the last element in the dataset, and it has an index to the next element. In the initializer, it takes parameters for all of those values except the next element. So back in dataset, we passed in a reference to self, which is the dataset object, and then the length of the data, which we will use to compute the last element, and the none code. Those values are all set from the parameters. But then we must set the next index, which will be the index to the next valid entry in the data set. So we start at index 0, but then we'll need to iterate through the data set until we find a value that isn't the none code. That's what we're doing with this loop. When it is finished, the next field will point to the first valid data element, or it will point past the end of the list if there were no valid data elements. Now, iter just returns self in the iterator. That's required for this to work in Python. Let's look at next, which both gives the next element and lets Python know when it's reached the end of the collection. So we need to write this so that when the method starts, if we're already past the end of the collection, we raise an exception that tells Python we're done. So that's this code. If self.next is greater than self.last, raise stop iteration. So this is structured so that once we've given the last element to the client, we move the next pointer past the end of the collection. The next time this method is invoked, we raise the stop iteration exception, which is how we tell Python we're done iterating through the collection. The rest of the method returns the next element and advances the next field. So we get the next value from the iterable, and then do something similar to what we did in the initializer. We iterate through the client, ignoring all entries that are the none code until we reach the next valid entry, or we're one past the end of the collection. At the end, we return the next element. At the bottom of this program, I've created a number of tests that set up different configurations of data and loop through to validate that the iterator is always returning only the valid data items and all of the valid data items. This is how we can use an iterator if we've written the iter and next methods correctly. Our variable data references an iterable, an object of our dataset class. So we can use the for variable in collection syntax. Here I've written for element in data, and that will return one element in the dataset at a time, ignoring the none code elements. If I run the program, which simply prints out the elements, you can see the NA elements were ignored. Now, there are times when we can't iterate using a for loop because we won't be accessing the elements all at once. In that case, we can manually create the iterator and manually obtain the next element. This is closer to the way we would implement the pattern if we didn't have built-in language support, although we're still going to use some built-in Python functions. To create an iterator, we send our iterable to the iter function. So I have written data iter, which is of type dataset iter, equals iter data, where data is our data set. So we pass the iterable to the function iter, and that returns an iterator. That invokes the double underscore iter function of the iterable. And then, because the iterator raises an exception when it is finished iterating, we must enclose the call to get the next data element within a try except block. So we write try, colon, and then the code that might raise an exception. And then except, and the code that handles the exception. This is another sort of flow of control from what we've seen before. If the exception is raised in the try block, we jump to the except block. So within try, we invoke next and pass the iterator to next. This will return the next element in the collection, so we assign that to element. And if that worked, we're still in the try block, so we can process it. Here I'm just printing it. But if we were at the end of the collection, then the exception was raised and will be in the except block. In the except block, I'm just setting a Boolean flag to true so that we stop looping and attempting to access data elements beyond the end of the collection. So that is the iterator design pattern as implemented in Python. I recommend that you write a set of iterator classes yourself. Start with something very simple. Perhaps simply wrap a class around a list and write an iterator to iterate over that class, visiting every element in the list. That way you won't worry about any strange iterator code. You'll just visit every element sequentially. Once you have that working, try something a little more complicated, such as visiting every other element in the collection or visiting the collection backward. Have fun with it.